Hello, everyone. We're going to get started. I am Maria Silveira, and I have the pleasure of serving as your moderator for today's webinar. On behalf of the USDA Climate Hubs and the Long-Term Agroecosystem Research Network, I'd like to welcome you to the third presentation in the series of 11 webinars focused on grazing land management and soil carbon. The goal of this series is to provide an update on the knowns and unknowns about the influence of management on soil carbon dynamics in grazing lands of the continental United States. Today's presentation will be followed by a short Q&A section. So please type your questions for the speaker in the Q&A tool at any time, either during or after the presentation. Today's webinar will also conclude promptly at 45 minutes past the hour. The title of today's presentation is Can Soil Organic Matter Really Be Changed on Grazing Lands in North Carolina? And today's speaker is Dr. Alan Franzlubbers. Dr. Alan Franzlubbers is a research ecologist with the USDA-ARS in Raleigh, North Carolina. His research is mainly focused on soil ecology and management. He has a leadership role in the USDA Southeast Region Climate Hub, and he also serves on the board of directors for the American Forage and Grassland Council. With that, Dr. Franzlubbers, the floor is yours. Thank you.
Good day. My name is Alan Franzlubbers. I'm with the Agriculture Research Service in Raleigh, North Carolina. Glad that you could join me today on this nice, warm, and humid day that is representative of the region that I'm going to speak about. The question here is, can soil organic matter really be changed on grazing lands in North Carolina? The southeastern U.S. is a region that's warm and humid, as I mentioned, and it harbors a lot of timber. That's the dominant land use in the region, but a quarter of the area is associated with agriculture, and that is divided roughly equally between cropland and pasture land, but it depends on which state and which apparent region. Soils in the southeastern U.S. are considered relatively low in organic carbon. That's partly because, or mostly because of the climate, which is warm and humid. That causes a lot of decomposition, but gives great potential for photosynthesis and the accumulation of biomass. So it's a balance. The soil organic carbon is always a balance between the production of plant material and the decomposition of that plant material into soil organic matter. And so regions that have high potential of organic carbon are not always related necessarily to the climatic conditions, because it's the balance between the production and respiration that occurs. Well, the conditions in North Carolina, I'm residing here in Raleigh, North Carolina. And I'm going to talk a little bit about some results across the whole state, starting with the coast, where this is represented the climatic conditions in Wilmington, where we have precipitation and potential evapotranspiration associated with this location at relatively low elevation of 30 foot above sea level. Moving to the Piedmont, represented by Oxford, North Carolina, and it also has high evapotranspiration in the summertime and relatively even precipitation during the whole year, and higher elevation, a little bit cooler temperature, and then cooler temperature further into the mountains, represented here according to Waynesville up in Haywood County, where we also have this peak of potential evapotranspiration in the summer and relatively even precipitation. So we see that in all cases, there's generally an excess of precipitation in the winter, in the spring months, and then tends to be a deficit of precipitation in the summer months. The state soil is sisal. It's an ultisol formed from intense weathering and leaching processes that result in a clay-enriched subsoil. There's a perception that tall, deep-rooted grasses will promote deep accumulation of soil organic carbon. And certainly the root distribution with tall, deep-rooted grasses is very deep. And Dr. Weaver in the Sandhills of Nebraska showed this very clearly in this image here between big blue stem and switchgrass, where roots were penetrating very deep into the soil profile. And those roots are penetrating, they're accessing water and nutrients, and they may be depositing carbon, but of course, again, it's the balance between production and decomposition that leads to soil organic carbon change. He measured also the root mass in the soil profile, and in the top 6 inches, there was almost 75% of the root mass that was occurring. So most of the roots were being in the top 6 inches, even with these tall, deep-rooted grasses. And then even in the top 12 inches, the top foot, there was already 90% of the roots represented, and then only 10% and at deeper levels. So obviously the deep-rooted grasses are important, but it's their decomposition and their production, that balance between them, that determines soil organic carbon change. And that's what we should be focused on, is soil organic carbon change, and not with the carbon that was already there in the profile. And that is part of the assumption and the design of root zone enrichment, where I'm trying to separate out the influence of management-induced factors, such as the planting of a species of grass, how the grass is actually managed and fertilized or grazed or harvested, and that which is there naturally through pedogenic processes. So there are some assumptions with this approach. And the first assumption is concentration of soil organic carbon below 12 inches is affected primarily by pedogenesis and not by contemporary management. This pedogenesis is a factor that is evolved over millennia, and that carbon is present deeper in the profile, but it's not something that we can assume is going to be changed because it's simply there, whereas management-induced factors occur primarily in the top 12 inches. The second assumption is that historical degradative management would have led to low surface soil organic carbon. And this is very true in the Piedmont region of the southeastern US, where I've spent a good deal of time. And the soils have been highly eroded, and it's a good assumption that there's degraded soil condition under historical management. The third assumption is that bulk density is inversely proportional to soil organic carbon. This simply states that as soil organic carbon increases, bulk density is going to decrease. And this is something that we need to take into account, because if soil organic carbon is increasing, we are getting less of the effect on a total mass basis, because the bulk density of the soil is also decreasing. But that bulk density decline is very good for getting water into soil, for soil to be able to hold on to the water, for microbial activity, for other faunal activity in soil. So reducing bulk density is a good thing, because obviously it's also good for plant roots to explore the soil and obtain their nutrients. The fourth assumption is the mathematical fit of the soil organic carbon depth distribution is relatively accurate. And this is something that I'm going to show you here in this image here, where the description of the soil organic carbon concentration indicated by these points that were measured deeper into the profile. These are the points, and then this line was fitted to these data through this equation here of STBA equals A plus B times E to the power of K times D. And I'm going to explain those terms, but the STBA is a function, or is soil test biological activity. This is the active portion of soil organic carbon. This is just used as an example. Okay, so this equation can be parameterized with various numerals that are here, then fitted to these data specific to this graphic. The 47 represents the STBA concentration that occurs deep in the profile, where it doesn't change anymore due to management. And the 957 is the amount of carbon, or STBA, that actually is occurring near the surface. And that's the total pool of soil test biological activity that can be mineralized. And this function here, this nonlinear rate coefficient, is determining how fast this decline in soil test biological activity occurs with depth. And of course, this example is for biological activity, but you could also use it for soil organic carbon. And I use it for that determination in the subsequent slides. But to give you an idea of how this function is then parameterized and utilized as a way of calculating, we're using this concentration at 12-inch depth as a baseline condition, and then this polygon in red is then used as a baseline condition that is subtracted from that which is accumulated in green which is really due to the management or the plant, the contemporary plant production and its deposition of carbon in soil. So this is the total where we have the root zone enrichment being subtracted from that total, and then, well, and then that leaves the baseline condition. So really what we're trying to do is calculate the total and the baseline and then get to root zone enrichment. I'm going to show you some results from a survey that I conducted across North Carolina on 25 research stations in the Flatwoods, the Coastal Plain, the Piedmont, and the Blue Ridge. The average conditions in the Coastal Plain look like this. We took samples at 3 different depths, at 0 to 4 inches, 4 to 12 inches, and 12 to 24 inches. These were from 36 fields from 9 research stations only under conventional till cropland. And these data points were then fit to a function, and that function is a nonlinear function, just like I showed you for soil test biological activity, but now I'm using soil organic matter percent as the response variable. Well, we also measured under grassland, and these data points were observed, and then a regression line fit to that, and we could calculate then the response of the root zone enrichment from that. No-till cropland happened to be somewhere in between those two lines there, and woodland was outside of it, where there was actually greater soil organic matter accumulation near the surface, and they all declined with depth. Now at the 12-inch depth, that's the baseline condition, and each of these curves has a different baseline condition. They didn't all converge to the same point. Sometimes they do in different scenarios, but in this case, they didn't converge to the same point. And that means that each of them had different pedogenic conditions to start with, and that's important to take that away. These were 112 fields divided among 4 land uses and the distribution with depth. In the top 6 inches only, we could make a calculation of what is the organic matter concentration. So we've done that here. Conventional till cropland had 1.5% soil organic matter. No-till had 2.3%, grassland 3.4%, and woodland had 6% organic matter. So you can see that actually land use has a really strong effect. There's a fourfold difference between woodland and conventional till cropland. So we have low soil organic matter partly because of the management systems that we've deployed on the land, but also we could have higher amounts of organic matter if we give the proper management. And you can see that grassland is one of the higher ones. It's not the highest, but it's one of the highest in the coastal plain. Now I'll move to the Piedmont region, and the same curves can be shown here. They generally follow the same pattern. They're closer to each other at the baseline condition indicator here at 12-inch depth. And so that has an impact on the calculation of root zone enrichment. But at 0 to 6-inch depth, again, we can calculate the amount of soil organic matter that occurs. And in general, they're roughly the same levels. The grassland actually being the exact same level in the Piedmont and the coastal plain in this study. And the woodland tended to be decline a little bit, and the no-till cropland following the same trend that occurred. Now, with that in mind, we can actually start calculating the root zone enrichment of the soil organic carbon in each of the different regions. And this bar graph here shows that conventional till cropland has some root zone enrichment of soil organic carbon. It's not set to 0 like in other types of calculations, but it has some root zone enrichment. The no-till cropland has even more. The grassland has equivalent to the no-till cropland, and the woodland has the greatest amount of soil organic carbon. That is due to relatively recent management, not due to pedogenic processes. We move to the coastal plain, and the same general trend occurs, but there are some slight differences here in that there's a separation now statistically between grassland and no-till, where grassland has greater root zone enrichment of soil organic carbon, and it's the same as under woodlands statistically. Obviously, it looks like it's a little bit different, but statistically, it's the same. We can also look at the Piedmont and the Blue Ridge regions, and the same general trend occurs. So therefore, we can basically conclude that land use is having relatively, in a general sense, the similar effect independent of the physiographic region. And we can see that in this case here, we have clear separation among all 4 land uses in the Piedmont, where they're statistically different from each other, increasing with this, what I would consider an increasing conservation gradient from conventional till cropland to no-till cropland to grassland to woodland. And in the Blue Ridge, there were no differences between grassland and cropland again, but they were much greater than in conventional till cropland. Well, if we put these all together into all of the 25 sites, we can see that there's a clear difference, a statistical difference, that the no-till cropland has greater root zone enrichment of soil organic carbon than conventional till cropland. Grassland has greater than no-till cropland, and woodland has greater than grassland. That's across all 25 locations. If we shift now to the calculation of root zone enrichment of total soil nitrogen, this would be the amount of nitrogen that is in the soil, but that isn't necessarily readily available to the plant because the microorganisms must mineralize this. They must transform that organic nitrogen into inorganic nitrogen so that the plant can use it. But there's a potential reservoir that can be utilized, and the no-till cropland is storing more of this nitrogen in an organic form, and the grassland is storing even more. And interestingly, the grassland stores the greatest amount, even compared to the woodland, because the woodlands aren't fertilized. There may be a little bit more nitrogen starved. They're not accumulating the nitrogen as well as the grasslands are. And if we put this onto a basis of a 50-year period, we could say that every year the conventional till cropland is actually sequestering 7 pounds of nitrogen per acre per year, whereas no-till cropland is sequestering 15 pounds of nitrogen per acre per year, and grassland sequestering 22 pounds of nitrogen per acre per year. This is a significant amount of nitrogen that is actually invested in the soil for the future, and so landowners can actually utilize that nitrogen in the future rather than have it a low amount, such as in conventional till cropland, that is not being built up nearly as rapidly and that is not available in the future. So we can look at the land use effects on soil test biological activity, and the same general pattern that is occurring. There's an increase from left to right, from conventional till cropland to no-till cropland to grassland to woodland. This one actually isn't statistically significant in the flatwoods region. If we move to the coastal plain, it's also not statistically different, but there's this general trend that's occurring. And then in the Piedmont, all of them are different between conventional till cropland and no-till, and then grassland being the greatest, but it's not any different than the woodland in that case. And then in the Blue Ridge, we have statistical differences among all 4 land uses, and across the land uses, we would say that that grassland is increasing in the root zone enrichment of this biologically active fraction of organic matter, going from the lowest elevation to the highest elevation. And that's a function of the climate, and that's interesting to know. The relative effect across by land use is consistent, independent of the physiographic region, but physiographic region does affect the absolute amount. And across the sites, there is this strong tendency similar to the total nitrogen, where there's greater amount in the no-till cropland than conventional till cropland, greater amount in the grassland than no-till cropland, and this being the highest level even compared to the woodland. The final study that I wanted to share with you, because it has some relevance, is 92 tall fescue fields that were sampled not only in North Carolina, but in surrounding states too. And I'm going to bring your attention to 2 factors: the forage utilization, where it's under conventional management, such as continuous stalking and occasional hay harvest, versus improved with utilizing rotational stalking. And the second factor is pasture age, the age of the pasture. And those are the 2 factors I'm going to focus on, but we also looked at the influence of elevation and soil texture in this study. Cores were collected, 8 cores in a relatively small area, and those were replicated 4 times, so we got a really good estimate of the amount of carbon and nitrogen that was stored in the soil. And this is the effect that occurred. The soil organic carbon, the absolute amount, not the root zone enrichment, but the absolute amount in the top 4 inches as affected by pasture management age. And you can see that there's a great increase in organic carbon that occurs in the first 10 years or so, and then it starts to stabilize and accumulating very slowly thereafter. So there seems to be some accumulation that's occurring even with very old pastures, but the rate of accumulation is much greater early in the pasture development. And for total nitrogen, there's a large increase that occurs early, and then a less dramatic increase with time. And we can then calculate the amount of nitrogen that is actually being sequestered per year. In this case, in the first 5 years, it'd be 72 pounds of nitrogen per acre per year, and then 48 during the 5 to 10 year period, 24 pounds per acre per year in the 10 to 30 year period, and 14 in the 30 to 50 year period. And on average, over a 50-year period, the average accumulation is 27 pounds of nitrogen per acre per year. This compares very similarly to the effect of the nitrogen calculated by root zone enrichment over a 50-year period in the previous study, which was 22 pounds of nitrogen per acre per year. So just to finalize with some the forage utilization effects, we see that total organic carbon was increased with improved management than conventional tillage, conventional management, and that particulate organic carbon was also increased. Cation exchange capacity was increased because organic matter is a source of exchange sites for cations, and so it's not only determined by the texture but also by organic matter. And the sieve soil density decreased, and that's because the organic matter is negatively associated with soil organic carbon, and that a lower density means that there's greater porosity and availability for roots to penetrate and explore the soil. So in conclusion, I wanted to state that soil organic matter and soil biological activity were highly stratified with depth under all land uses. Compared with cropland, grasslands clearly are storing greater quantities of carbon and nitrogen, so there is an effect of grassland management. Better pasture management has potential to improve soil organic carbon and nitrogen, but evidence is relatively sparse in North Carolina. So therefore, research is ongoing to better understand the effects of pasture management on long-term soil health development. Well, finally, I wanted to just conclude by stating, try to answer this question. Can soil organic matter really be changed on grazing lands in North Carolina? And I believe that the evidence that I've presented would say that yes, in fact, there is a possibility that certainly compared to other land uses, grasslands are storing quite a bit of carbon, and they may not be changing that carbon. If there's a mature pasture, it may not be changing dramatically currently, but over time, over the lifetime of a pasture, it changes quite dramatically. And I believe that there are opportunities for management differences to affect this change that is occurring, and we're conducting those studies to find out if it's really changing on private lands in North Carolina and then in surrounding regions as well.
Hey, Alan, there's a couple questions, and just want to remind everyone, if you can please type your questions in the Q&A tool, that will be a little bit easier for me to read your questions to Dr. Franzlubber. Alan, one of the first questions that a few individuals are asking is if you can elaborate a little bit more about the nitrogen fertilization regime for the croplands, both the non-till and conventional till and the grasslands, if you can just provide a little bit more detail.
Sure. Thanks. Good to see you, Maria, and thanks to everyone for attending. The fertilization of the crop, the grassland, the no-till cropland, and the woodlands, they were all quite variable. The woodlands were in generally not fertilized. The cropland was fertilized according to kind of state specifications. This was a survey. This was not a research project that was developed at time zero, and that we then made fertilization applications and measured organic carbon change. It was after the fact. I went into all of the research stations and so those croplands may have been cropped for 50 years. They may have been cropped for 15 years. And so there were differences there. There were differences based on the crop. Peanut not receiving any nitrogen fertilization, soybean not receiving any, corn, of course, receiving a considerable amount in most cases, but it was variable, and it was variable over time and variable among the locations. As far as the grasslands, they were generally minimally fertilized, I would say, and that was highly variable as well because not all of them were grazed. And I saw some questions there about whether it was grazed or hayed or not. And it was a mixture. These were from research stations, and we only have, let's say, about a quarter of the stations that have ruminant livestock. And so there was only grazing in some cases, but not in all.
And also, a kind of related question, whether the species was tall fescue or if you had warm season grass, if you can.
Yeah, it was a big mixture as well. So our tall fescue tends to grow well in the Piedmont and the mountain regions, the Blue Ridge, and less so in the coastal plain and flatwoods. And so we in the coastal plain and flatwoods there was a diversity. Sometimes it was Bermuda grass, sometimes it was centipede, because I have to admit that sometimes I had a struggle to find grass, and so the grass happened to be just a cut grassland near the station building. So, essentially an, say, minimally managed lawn situation.
Also a related question about, and it's more a comment, and the individual is asking your opinion about whether rotational grazing can be considered a improved practice. And he or she wrote that they've seen fields full of weeds with muddy soils, and that was considered rotational grazing. So to what extent that can be considered improved management practice?
Sure, it's a great question, and it's one on top of many people's mind, of course. And when we try to put this stocking method into a category, it really becomes problematic, because stocking method, say rotational stocking versus continuous stocking, this is a broad categorization. Management within those two categories can vary quite greatly. You can have a different stocking rate, you can have a different season of grazing. The deferment can occur at different times. All of this is actually, really complicated. Now, is rotational stocking a good improved management? It can be. I believe that because the land manager pays attention to the animals and actually what they're consuming and where they're moving to, I believe that potentially it is a very improved method. But that doesn't mean that it's implemented that way in all cases. And I think it's really difficult for us to find. Let me just state that the preliminary evidence that I collected already would suggest that continuous stocking can lead to just as high organic carbon as rotational stocking, if continuous stocking has an appropriate stocking rate and the grassland is managed appropriately. So again, it's not whether it's rotational or continuous as categorizing it as improved. It can be, but it isn't always that way.
Thank you. And another question also related to the stocking methods is, to what extent that improved grazing affect the number of livestock kept or produced on a given area of land overall? So the productivity, animal productivity in those improved versus to what extent that affect animal production?
Okay, I think I understand the question. So if in fact we can actually increase the productivity of the land with a stocking method, yeah, I think there is a possibility. When we can allow, so resting of a forage is important. There's no doubt about it, because we need to have a good root system where the carbohydrates are in reserve, and so that we can actually produce forage. The old saying that you have to have forage to produce forage. Well, there's a lot to that. And that you cannot simply, if you have continuous stocking and you have a golf course that you've developed, then you need to have precipitation daily, or every other day. And so those are the conditions. If you don't have that, then you're running the risk of ruining your forage stand. And so forage stands will change over time. If you have a tall fescue field, and you have the endophyte, the wild endophyte, it's possible you can keep it longer than other forages. But even with that condition, with the endophyte, I think you can graze out tall fescue. And so other species will come in. Will those be more productive? That's for you to find out. But in general, we don't see those are desirable species coming in.
Thank you. There's also a question about the cropland treatment, if the no-till was actual no-till or if it was infrequently till, and if so, for how long?
Right. No, that's a very good question, and all of those details are important. So in general, the no-till, the few farms that are research stations that had this no-till, they were actually implementing the no-till for a good at least 25 years, and in several of them had over 30 years of continuous no-tillage. Now, it's on a research station, and so there are possibilities that staff have turned over, and there wasn't a good recollection of what kind of information they were giving me. But I would say generally say that these were relatively long-term no-till in the cases where we did have them, but we didn't have as many no-till fields as conventional till fields on the research stations in North Carolina, because particularly in the coastal plain and flatwoods, we don't really see a whole lot of adoption of no-till practice.
Thank you. There's also a question in the chat about the depth that you chose, the 12 inches. What was the rationale, and if you think that would be applicable to other regions in the country?
Great question. I love this question because I believe that it is applicable to other parts of the country. What I really want to explain is that the primary root zone, where the majority of roots are going to reside, are in the top 12 inches. I challenge everyone to prove that wrong. And so once we get those data, let's share them and have a good debate on that. There are roots that go below 12 inches. I'm not disputing that. It's the magnitude of those roots, the root mass that occurs. The root mass is generally in the top 12 inches. Now, in this approach, I actually sampled 0 to 4 inches, 4 to 12 inches, and 12 to 24 inches. And with that, then I could create this nonlinear regression line that then fit those data to this. And then I would be able to project what is that which is pedogenically controlled versus management controlled. And that's the real key behind this presentation is that soil landscapes have a pedogenically controlled given carbon content, total nitrogen, biological activity, all of that is developed over millennia. And that's something that was given to the landowner. That's not what the landowner is changing. What we want to focus on is what the landowner can change. And that's where that root zone enrichment comes in.
Thank you. There's also another question. What would you say to someone using this research to support land conversion from grassland to woodland to increase carbon capture?
Could you repeat the question, please? I'm not sure.
Your opinion about someone who might use your research to support the idea of converting grassland to woodlands to increase carbon capture.
Right. Okay.
I guess the trade-offs and benefits.
Yeah, it's a good question. When I first started these land use comparisons, I thought that woodlands would have the most soil organic carbon, and in fact, in this research station study, it did. But subsequently, I've made measurements on private farms, and there's actually more carbon. Well, as much carbon under grasslands as in woodlands on average, let's say. And for total nitrogen, as the data I showed you here as well, it's actually greater under grasslands than under woodlands. So yes, it's always possible to convert grassland to woodland. And if there's a good reason to do it, then go for it. Absolutely. But I think there's also an opportunity to say that grasslands have this more enriched type of organic matter that is actually of greater fertility than under woodlands. Anyway, I've got some other research that's in the pipeline. I'd like to comment further, but I won't do that right now. But I would say that there's a great opportunity if we were to use grasslands and cropland in rotation. I think that's where the real value is going to be as far as improving fertility for the cropland, actually. So I'll leave it there.
And I have to apologize. I'm trying to group this question into something that's but it's all over the place. So I'm going to go back to the issue about the soil carbon sequestration. So the question is if carbon and nitrogen sequestration are related. And if so, does that signify an increase in biomass could be related to increasing nitrogen and carbon sequestration?
Carbon and nitrogen sequestration are related. In general, they're related by an empirical relationship is around 10 or 12 parts of carbon per part of nitrogen. But in this land use comparison, I've certainly found over and over again that woodlands tend to have an even larger ratio, where it's 15 to 18 parts of carbon per part of nitrogen. So the idea is that nitrogen in the woodlands is being cycled rapidly, and so there's probably a really considered a starvation of nitrogen. Nitrogen is there, the trees do grow, but they're giving up nothing. They're really holding on to that nitrogen. Whereas grassland, perhaps there's some giving up that could occur. And that's why a grassland does not need to be fertilized intensely every year. It's just when you have a mature pasture, nitrogen is being cycled. And when you have a mature pasture and you have plenty of carbon in the ground, that means that you also have lots of nitrogen in the ground, and so it becomes cycled. And that's why there's this idea that we could maybe back down on some of the nitrogen inputs in grassland systems.
Alan, since you mentioned this comparison between the woodland and the grassland, one of the questions here in the chat was, to what extent maybe prescribed fire in the woodlands have influenced some of these responses?
Good question. I'm not aware of many events where the prescribed fire was implemented, but it's possible that they were in the past. I think that there's an opportunity with prescribed fire. Then we're changing the dynamic of the woody litter that falls to the ground, and so that is an important aspect. I think fire could accelerate some nutrient cycling. Certainly, there could be some base cations that are reincorporated, and that could be beneficial because in long-term woodlands, the base cations are really at a low level. We've measured this deep in the profile, and they're just at a very low level. So there is a possibility to accelerate, I think, nutrient cycling with prescribed fire in woodlands. Yes.
Thank you. There's also a question about, since the grazing management vary across the different sites, this individual is asking if your opinion, if a functional indicator for improving grazing lands could be something like grazing stand, plant type or variety, or plant height, if you think that could be a good indicator of the type of grazing management.
Yeah, I think plant height could be a good indicator. Of course, the forage stands are variable. It depends on the species, but I believe forage mass, the residual mass that you have behind a grazing event, I think that should be a key consideration. We don't want to leave too little forage mass behind because there are a lot of effects that occur. So when the sunlight hits the bare ground, it bakes it. It causes crusting, even with some organic matter enriched soil there. So there is a negative effect and of course the temperature gets high, the roots need to grow deeper, and they don't have much forage, residual forage there, so they don't grow deeper because they don't have enough reserves. So all of that can have a negative cycle. So I think the residual forage mass is a good indicator, and so plant height would be that one simple tool that you could use for that.
Apologize, Alan. You're being bombarded by quick questions. There's lots of questions in the chat. Do you have any data for silvopasture systems? This person is asking. It will be interesting to take these measurements in silvopasture setting.
We have a silvopasture research demonstration site in Goldsboro, and it's in the coastal plain. And we've made some measurements. We haven't published greatly on it, but we have some measurements. And of course, silvopasture again is a category, and there are many types of silvopasture. Are you having pine trees, or are you having deciduous trees? What is the arrangement of those trees? What is the forage species? So there are a lot of different arrangements that can occur. But I think in general, the grasses are showing that there's good accumulation of organic carbon and nitrogen. Trees provide shade for the animals, so that's a benefit just by itself. And then I think that the recycling, because the animals can move, they can move nutrients around as well. Silvopastures, I think we definitely need to explore that area.
Thank you. Going back to the no-till croplands, This person is asking if you see any evidence of vertical movement of soil organic carbon across different depths.
In general, I would say no. Of course, you can get soluble carbon movement, but when carbon and nitrogen are solubilized, they're also accessible to microorganisms, and we have soils, an environment where that decomposition can occur rapidly. So there, yes, potentially there could be some movement, but it just doesn't seem to happen. And if we have decades of management that continues, we see the same low levels of organic carbon and nitrogen below 12 inches. It's simply not changing within the decades that we can measure. Now, over centuries and millennia, yes, perhaps it's going to change, but we just don't simply have that time. And the opportunity for using this root zone enrichment technique is really because of our rushed need for these data to make good management decisions.
Thank you. Most of the finds that you share with us today are from Altis soils. So the question is if you expect to see the same type of improvement in that 10-year time frame before a shift to marginal gains. How would that change if it was a different soil type?
It's a great question. I think the concept works in that we would find large changes initially and then smaller changes after a few decades. I think that part of the concept is legitimate, but I don't know what the numbers would be like. I think we just need good research designs to be able to tell us that. I think there's certainly we need long-term research station studies, that we do need them, but we also have this great opportunity to, if we could assemble a sampling on a diversity of farms in a region, this can provide us realistic estimates very quickly. And again, we need large numbers because there are the possibilities of making misinterpretations. We need to be sure. So we shouldn't rely on a couple of fields. We should rely on dozens of fields.
Now, a little bit of a broader question. What are the next steps for your research in this area?
Yeah, well, I've led into that. So I think right now I'm really focused on gathering information with willing participants. Of course, many might say that it's a biased approach. Well, in some ways it could be biased, but in 2 years ago, 2 winters ago, I actually sampled across the state of North Carolina only on private farms. I went to 207 private farms and sampled 1 or 2 fields on their farms. I asked the county extension agents, we have 100 counties, I got into 70 counties and sampled these fields. I believe it wasn't biased because it relied on 70 different individuals to recommend a field for me, a farmer, and then I'd use the same approach across. So those data are ready to be assembled and published. We're just waiting on a few farmers to give me some management history. So that is in the works. I think we have great opportunity there.
This question is not in the chat, but it's my question to you. I know that you haven't finished this analysis, but to what extent do you think that management will influence soil carbon in this large data set that you just collected?
Yeah, I think that management can have an impact. And I would say that if we're looking at, say, starting a pasture versus one that is 50 years old, I would say that magnitude is roughly 50 tons of carbon per hectare. And so I'm using tons per hectare because those are the units I can use. If I use the units that I used in the presentation of metric tons per acre, metric tons of CO2, that would be then 75 metric tons of CO2 per acre. The management part, I believe we can change. So that would be the duration of the pasture. That would be 75. For management, I believe that over a 50-year period, a management effect could be roughly up to 20 metric tons of CO2 per acre. It's not going to be as large as the duration effect, even of a relatively poorly managed grassland. I just have to say that. That's my impression, my hypothesis moving forward right now.
Maria, I think you're muted.
I'm sorry for that, Alan. I think we are reaching the end of the webinar. Appreciate your presentation, and I also want to thank everybody for attending this section of the Grazing Land Management and Soil Carbon webinar series. Please note to the participants that a link to the recording of today's presentation will be available on our webpage. And also, please plan on joining us on September 9 for our next webinar. And the title of the webinar will be Evaluating the Role of Grazing Strategies on Plant Production and Soil Health Across a Decade Timescale by Dr. Marilyn Swans. We hope to see you then. Thank you so much.